definition of agents. I particularly like the one proposed by Barandyan and others in 2009, and this has three components. And the first is that agents should be individualized. So they should be kind of separate from other things, and you should like be able to say, okay, this is the agent, and this is not the agent. They have the capability to act. I think that's quite important. When we talk about agents, we always think about things that can cause stuff or do stuff, make some things happen, and not only have things happen to them. And the last thing is that agents are goal-directed. Often that's kind of connected to self-sustaining, or it's also called normativity. But yeah, all these things are kind of subsumed into goal-directedness. And this is basically, so Barandyan also did a literature search, and it's showed that it's kind of compatible with most definitions of what an agent is in computer science. And the other feature of this I like is that basically all living organisms, and also, in my opinion, also many current robots already satisfy this condition. Okay, so the current agent model that I think you find in things like the control loop or feedback loop, sometimes called perception action loop or sensory motor loop, or also in pure MDPs or reinforcement learning. In my opinion, all of these models basically use the kind of all of these approaches use kind of the same agent model. And since control theory and AI are quite established and successful research fields, I would say this agent model is also very successful. And what does this consist of? It's basically two interacting stochastic process, and we have variables that are called the memory, that's M, sensors, which are produced by the environment or that the agent receives from the environment, actions that the agent generates, so they only depend on the agent memory, and we have the environment itself, which is on the other side. And the process is then described by some kind of transition probability, which produces actions and next memory states from past in response to sensor values, actions, and last memory state. And the environment is also has a similar transition probability. And yeah, so in this case, what we can say is that this definition of Barandyan et al. Is kind of trivially satisfied. So it's more satisfied by construction. There's not, we don't have to do a lot of analysis to find these, because in the beginning we already assumed that we have two interacting stochastic processes. So it's easy to say, okay, we have an agent and we have something else, which is the environment. And in this way, this agent is already individualized. And of course, the capability to act, we have also put it directly into the model, because we just designate these things as actions, and they influence the environment. So they also have this property of maybe making something happen because they change the environment. So that's what they make happen. And the goal-directedness is maybe less explicit in this model, but usually realized by some kind of reward or utility function. And we also basically know how to do this. So we can make agents according to Baronian's definition. And we do that also a lot of times. I mean, that's what a reinforcement learning agent is, an agent according to this definition. So this seems to be pretty easy from this perspective, at least. But if we look at universe models, we can see that basically the standard model and general relativity, they're all dynamical systems. So in some way, they're stochastic processes, like deterministic stochastic processes, maybe. And yeah, so that's basically all I'm going to say about physics. I'm just going to say that I'm just going to assume they're a stochastic process. And what I practically look at when I try to find like an agent definition is more discrete dynamical systems, because for me they're easier to deal with. And as you may know, we can always kind of approximate any continuous system with discrete systems. So I hope I can get away with it. If not, then that's my problem, I guess. The other thing that is good about discrete dynamical systems is that they're often Turing complete by themselves. So at least computationally, we should be able to, like if we need computational capabilities, we will usually find them in these systems. So what I do personally in my research is that I just assume that finite or at least discrete dynamical systems are enough to contain agents in the end, like, because oh yeah, what did I say? Yeah, so this is what I usually do to model a kind of to think of a universe. I just take the finite or countably infinite state space, and I define some kind of dynamical law by defining a Markov kernel. And maybe I specify some initial conditions, and then we get trajectories, and those are then different evolutions of these universes. And yeah, the graphical representation of this is just one stochastic process. So some examples of this, maybe you know, famous examples are the cellular automata. Oh, that was not the plan. How did I? So in these cellular automata, you see all kinds of interesting structures, like these gliders. They can move around and they can be produced and disappear. And you can make bigger gliders with lots of massive constructions and other weird things. Yeah, and at some point you can also build a Turing machine inside such a system, which is how you prove that these things are universal. Turing complete. So yeah, you see like pretty complex structures. So this is also, I guess, I mostly show this to convince you that maybe discrete dynamical systems are already enough to contain something like agents also, even though these things are probably not really agents. But at least they can move around and do complex things, and they can compute. So, okay, how do I get out of this? Okay. Isn't this the right button? Maybe not. Oh, okay. And here's another dynamical system, and that's a reaction diffusion system by Nathaniel Virgo. Yeah, and you see how these different concentration, or the concentration of chemicals creates creatures that can move around. Yeah, so these things may also already look like agents, or maybe agents. We don't really know. I think we don't really know, because we don't have a mathematical definition of this. So yeah, now we come to the more exit full screen. How do I make it full screen? Press 11. Yeah, I tried it. No. Sorry. Yeah. Okay. Wrong slide. Yeah. So now, so what I basically want to do is I want to start with a system like this, because that's a universe system, and then I want to, in the end, I want to have a mathematical definition of something that constitutes an agent within such a system. That's kind of my goal. And so what we like, I think what we have at the moment, as far as I see the research landscape, is two main approaches. And the first one is about the first one does basically tries to split the universe process into two processes and into an agent and environment. And the second one looks at basically spatial temporal patterns that are that occur in single trajectories of the universe, and tries to get find those spatial temporal patterns that are agents. Okay, so when you take this approach of splitting dynamical systems, what you do is you propose some criterion about how agents interact maybe with the environment, and then you find a split of the state space. So what you do is you create two new variables, E and M. You represent X, the state variable of the system, by a Cartesian product of two variables, which one of them is going to be the environment, one of them is going to be the agent, or the agent's memory. And then from this you derive the kind of sensor values and actions, and then you try to derive also the goal of these agents, and then you would have basically the same a kind of system that has the same features as the agent model that I described before. So you have some goal, you have individualization, actions, and also goal directedness. Okay, so this then schematically, this looks like this. You start with this process, you split it into environment and memory. Then from this you can find basically the sensors and the actions, which are just the random variables that actually influence the environment or the memory respectively. And then you check the criterion that you kind of need And then if this criterion says, no, this is not a good split into agents and into agent and environment, then you start again, you try another split. And but if your criterion says yes, then you try to infer the goal from this process. Some people have proposed ways to split in such a system in this way, and the first one is by Krakauer and Niels Bertschinger, who proposed non-trivial informational closure as a way to split these universes. And also maybe it's interesting to say that you don't have to split the universe in the same place at every time step. So you can choose a different split at every different time step if you want. Another way to split the dynamical system is proposed by Friston, who uses Markov blankets. And that basically means that since this system here is basically a Markov blanket in some way, he kind of says that every split into two such pairs is a kind of already is an agent, because it implies Bayesian inference and also some kind of goal directedness. But I would say this claim is a bit sketchy. We just proposed, published a paper on some problems with this Markov blanket approach. But he also has a newer version, so maybe it still works, I don't know. And another way to maybe split a dynamical system, but that hasn't been proposed yet, is maybe something from thermodynamics. I don't know. I sometimes think maybe that's possible by using kind of work. And I think there's probably different other criteria for doing these splits, but not many have been proposed. Okay, so to get goal directedness, once you have such a split, what you could use is inverse reinforcement learning, and that's probably the most straightforward way to do it. This is also related to the intentional stance by Daniel Dennett, and there's work by Simon McGregor, who tries to do this. Of course, you can kind of say that if you try to define an agent and then you say, well, I'm gonna say this thing is goal directed because I can describe it in a shorter or more efficient way if I assume that it has a goal. So this is basically the intentional stance, and also that's what you use in inverse reinforcement learning. You try to find some reward function that explains the behavior of this agent. But if you do that, you are kind of also assuming that there is this observer that looks at this process and tries to interpret it. Tries to find its goal and tries to describe it. But then, what is this observer? What kind of object is this observer? Is that not an agent itself? And then, how can you define agents by using another agent? That sometimes makes me feel a bit uncomfortable. But yeah, maybe there is a way to do this. So, like sometimes, so maybe one way is to say, if for any possible observer, this thing looks like an agent or has a goal, or describing this thing is more efficient if you use a goal, then that's maybe a way to get rid of this circularity. Another way to get goal directedness is maybe actually have goal directedness as one of this as basically the split criterion. So you kind of say that when you check your current split, you just say, okay, I'm only going to allow splits where one of these processes can be more shortly described by assuming a goal or something like this. Yeah. But yeah, I mean, I've never seen, people have not really done these things or worked these things through. Okay, so okay. So what I now want to talk about is maybe a problem that I see, at least with this splitting approach, at least with the existing ones, or at least specifically with the one that Krakow proposed. And I think it's something to keep in mind. I think with Fristen's work, you could avoid it also, if you so you don't have to do this. But the thing is that if you split a stochastic process into two, then you do that. If you split the entire process into two, then you have two processes, and you basically keep this split. You cut basically through all possible trajectories. You cut at the same place. So if let's take a look at this stellar automaton where time goes this way and you have space here. And maybe this one trajectory looks like this, and maybe we think, I don't know, these gliders here, maybe they're agents. So I'm going to cut along this. I'm going to cut this out as the agent and call the rest the environment. So maybe like this. But then if I change the if we change the initial condition, so this is still the same system, but a different initial condition, then I get a totally different trajectory. And then if I still keep the split, then I'm probably wrong. I mean, because if the reason for the other split was that there was a glider, then this reason is not a reason for this trajectory. So here we would want to cut here, and this basically shows us that we shouldn't split the system once through all trajectories. If we are looking for agents, we should actually do this trajectory dependently. Probably. I mean, yeah. Okay. So a different approach is maybe to look at spatial temporal patterns. I'll talk a bit more about it in a second. And again, you do a kind of similar thing, and you try to find a criterion that tells you which spatial temporal patterns are individuals, and then you define actions in some way for these spatial temporal patterns, and also goal directedness. And all of these things have to be then compatible with the dynamical law, of course. So what's a spatial temporal pattern? Basically, it's just a specific, so it's kind of a subset of the variables in this dynamical system with specific values. And so you pick at each time, so you can pick at some certain times and certain places, you can pick the variables and basically freeze them and say, I don't care what the other variables are, I just look at, I just define this thing, and this is my spatial temporal pattern, and I'm going to say this spatial temporal pattern occurs in certain trajectories, and in other trajectories it doesn't. And then I can say some things about these spatial temporal patterns and try to say, okay, an agent is maybe a particular spatial temporal pattern. So, for example, if we use this glider, then we could say, okay, maybe every spatial temporal pattern, whenever this thing occurs in this universe, we have an agent. I mean, of course, this glider is not an agent, but I cannot draw spatial temporal patterns in much more complex systems because they are usually too high dimensional. Okay, so Yeah, the obvious advantage of this is that you can have, these agents can have different positions under different initial conditions, and they are not defined only by what happens also in other trajectories. Okay. So there's also some proposals in this direction, and the first ones were by Martin Biehl, who uses kind of ideas from autopoiesis to describe gliders, and he has kind of conditions on individuality and also a definition of action and perception for these kind of gliders. He doesn't have, he doesn't really say anything about goal directness. Like when I mean, he says basically when a certain spatial temporal pattern forms an individual, and that depends on the recurrence of certain processes or certain transitions from one time step and then again in the next and again in the next. But yeah, there's no, the main problem with this whole approach is, or with the current state of this approach, is that the definition of goal-directedness is still missing. I also proposed some kind of condition for individuality using some kind of local or pointwise version of IIT, maybe, very similar. And then tomorrow we will see work on actual causation and also IIT, or at least the perspective from IIT on this issue, how to get at least individuality inside a system. And I also proposed how to define actions and perceptions in the past for such systems, which maybe works all, but again, there's no goal-directedness. So I think until we find a way to define goal-directedness in these systems, all of this is still speculation, at least, because we don't really know what are the things, like if you want to check if something is performing actions, and you can check what these actions are good for, then it's really kind of sketchy. Maybe some other possibilities to do this is using a pointwise version of non-trivial informational closure, which we're maybe trying to do now at Araya. And another thing is maybe using some kind of pointwise partial information decomposition terms like synergy or redundancy. But I also don't really know where the right starting point for this is. Okay, so the problems with this approach, I would say, is that we have no consensus in the field. We don't really know which definition of individuality, which definition of action is actually the right one. We don't have a definition of goal-directedness. And I think the biggest problem, which is basically the reason for these other problems, is that we don't really know what you have to require from a successful definition of agents inside these stochastic processes. So when are you done? We don't really have a criterion. So in machine learning and AI, they can just use some kind of Kaggle competition or something and establish, oh yeah, okay, so this reinforcement agent, it works. So I don't really care whether you like the idea or not, but here we don't have anything like this. So we can't really say, okay, so my agent definition is better than yours because of this. Because we don't even know what this is. Like, what should it really do? At the moment, I think maybe the best way to find something that is a criterion for an agent definition is to try to use Darwinian evolution as a criterion. So basically you say, okay, if your agent definition, if you start with a dynamical system and you give me your agent definition, I find these agents in there, I look at them, how they evolve over time, and if I now find that these agents are basically subject to Darwinian evolution, then maybe you can say, okay, that's kind of convincing in some way, at least. But yeah, I tried to start some work in this direction. It's unpublished, but there's a video online you can watch. Yeah, so maybe this is a way. I don't know if there's a better way to do it. Okay, yeah, maybe one other thing is that these agent definitions should explain why this other agent model that just splits the system into agent and universe, or at least these models as stochastic processes that we use, why they work so well, because they apparently work very well. So if you, yeah, I think this has to be a result of this research. Okay, so now I'm at the end of my talk. What's the timing? 41. Okay, we have lots of time. Oh, well, then we will find something to do with it. So what's the summary? I think we know how to model agents. At least we know how to model agents that satisfy Barandrian's condition, and I think they're good agent models. I think the problem is we don't know how to connect these models to our models of universes. And yeah, the proposals that we have for doing this are all kind of ad hoc, and yeah, goal-directedness is not understood really well. And yeah, I said also that actions seem that a convincing solution for a definition of actions is also seems to require to have a good definition of goal-directedness, I think. Yeah, and yeah, the last point is the one that I just highlighted, that I think we need a way to justify one agent definition over another. And if we would have that, then maybe lots of people could propose agent definitions, and we would just make progress much faster than we did in maybe the last 10 years that I've been following this still very small research field. Okay, that's it. Thank you. Yeah, let's make sure.
Thanks for the talk. So when you talk about, say, things like pointwise information measures of various sorts,
yeah,
and trying to use those to define some trajectories or like spatial level patterns that qualify as agents.
Yeah.
Does it say anything, or do you have anything to say about the possibility that agents may like spring in and out of existence at random points, right? Like, could you have like multiple agents happening? What restrictions do you envision to accommodate or avoid or think about it?
So I'm not sure. I mean, I think on the one hand, I think actually don't really understand why it's a problem, because I would say it's almost like, from my perspective, it's kind of a requirement that agents can pop up out of they can basically pop up into existence and disappear again, because that seems to be what the actual agents in reality do. I mean, at least if you agree that there were no agents, let's say, I don't know, just after the Big Bang, then at some point between there and now, they must have sprung into existence. So I think that's also one problem of this definition of agent as stochastic processes. These agents, they can never die. Like, they are there from the beginning, and they will always be there. And that's of course not true for any real agent. Like, we also die, and or maybe not anymore at some point, but currently we still die. And so I think that kind of agents like this that pop into existence and then disappear, they're kind of, if your agent definition rules this out, then I think it's wrong. Yeah.
Can I ask a question, Martin?
Yes. Oh, yeah, yeah. I can't see you, but I can hear you.
So this thing about dying.
Yeah.
Wouldn't you agree that all the agents that we actually observe in biology have found a way to cheat death, which is to reproduce?
Yeah.
And so by your Darwinian evolution criterion, can't you imagine that self-sustaining might take the place of your goal-directedness, so that you don't actually need to define goal-directedness, but it might emerge from self-sustaining, cheating death, reproducing, and then the goals are always context-dependent, like sometimes you have to do certain things to survive, other times you have to do other things.
Yeah. I would say, I mean, I guess I just see self-sustaining as one goal. So I would say I would say even self-sustaining agents are goal-directed. Their goal is to persist, basically. So I think they still have to be, I mean, I think since even these self-sustaining agents, they can die. I mean, we can also have extinction of species. So and also I guess it's kind of not completely out of the question that all of life will disappear again. So I think you would still, like your agent definition would still need to allow for the possibility of death. And so that's one thing. And the other thing is that I guess I would say good self-sustaining is also a form of goal-directedness. Yeah. Does that answer the question?
Yeah, maybe.
Okay.
I don't think that all of life ever ended on this planet. Everything that's alive can be traced back. Maybe the dinosaurs, but not all of life ended and then it started again. I don't think that's the current model, or is it?
Yeah, no, that's true. So I think also you can, for example, you can view life as a single agent maybe, and then it didn't die. But I think, I don't know. I mean, I still think that it's possible that it could die. Like, let's say the sun explodes, then probably life. I mean, at least the possibility has to be there. I think. I don't know. But yeah.
Yeah, sure.
Okay. Yeah.
Marisa seems also have a question.
There were also questions. I mean, I take Manuel's question. Okay.
So a couple of probably general points. One probably have the last question. Why is goal-directedness so necessary? Why is there a random-based approach? I mean, the goal might just be, I have no glider, so I started, now there's a glider. The very, existence of the glider is the goal of the glider. So when it became the glider, that created the goal of being
yeah, okay, yeah, that's. But the thing is that the glider, for example, doesn't do anything to achieve this goal. So, I mean, or let's put it this way, if there's some obstacle for the glider, it doesn't know how to react to it. I mean, you could say, okay, but the glider.
It survives on perturbations and it dies because of
It's true, yeah. It does actually survive 3%. or 5. No, not percent. No. Of all the billions of interactions, it survives 5 or something. I don't know. No, the ratio is extremely small, but yeah, it's true. Yeah, so you could say then persistence is a goal. Yeah, I think that's fine. If you, yeah, I think in general it's fine to say persistence is the goal.
So the spatial temporal, approach can still be, used.
Yeah, I think so. I just don't. I mean, but it seems like, but what's the mathematical definition of persistence? Yeah. A stone is persisting and it's not an agent. Yeah. Yeah, it's yeah. I mean, like, yeah, this is one of these. I mean, the stone is basically a major example, but also it poses this problem. I mean, I agree that if you say basically the only goal is persistence, then the stone has kind of achieved it, and maybe it doesn't have actions. So maybe that's how you prevent it from being an agent. But yeah, that depends also on your action definition. Because you can also say, oh, well, but if I heat the stone and then I put it into a cold room, then it heats the cold room. Maybe that's an action. I don't know. It's yeah. So yeah, you do run into these troubles. I mean, I accept that these are problems.
Second point, why evolution? I mean, if you bring in evolution, then robots cannot be agents, right?
Yeah, kind of. Yeah. I mean, apart from, I mean, those that build themselves, they can do it. I mean, if the robots can build new robots.
So autopoietic robots.
Yeah, they would. Yeah, probably also be autopoietic. Yeah.
So autopoiesis is what you want, not evolution.
Yeah, maybe autopoiesis is a good yeah, maybe it's a, yeah, I mean, I would say it's maybe harder. I mean, like, okay, autopoiesis, okay, it's true. Autopoiesis is also one solution for this. I think you could use it, but autopoiesis is also not mathematically defined. I mean, so it's not a full solution. I mean, but yeah, I mean, that's what basically maybe Martin Biehl is. I mean, he's trying to build his individuality criterion on this autopoiesis. So yeah, people are doing it, but yeah, it's the same. I mean, actually, in some way, it's the same with Darwinian evolution, because we also don't really know. I mean, I don't know how to mathematically determine that some set of spatial temporal patterns is doing Darwinian evolution, but the same thing is true for autopoiesis. Yeah. There was there a question up there somewhere? Oh, okay. Yeah.
I have 2 points. One is in very ancient time, people were following animistic-like religions, and they were seeing like spirits or gods in almost everywhere. So it's like agents, and almost every single thing which was happening is because of some agent. So you can define, you can make a very different definitions of what agent is. That's the first point.
Yeah.
The second point is maybe define the level of complexity using entropy. So you have a spatial something which is happening in time and space, and which has a very low entropy, and define this as an agent.
Yeah, I think if it has a very low entropy. So does a rock have low entropy? If you cool it down, yeah. If you heat it up, no. Okay. So cold places have, so Antarctica, does it have a low entropy? I mean, yeah, it's a, yeah, yeah. I mean, in the end, but I understand. Like, so in the end, yeah, you could try and say like, okay, so if I find spatial temporal patterns or something that have like generally low entropy and keep this, yeah. I mean, like in the, I guess in the CA it doesn't really look very intuitive because you would, but I guess also it depends a bit on which entropy you measure exactly.
It was the Schrödinger's definition of life. Low entropy state.
Did he say exactly what he, the low entropy state? Yeah, but did he say exactly what is the thing you have to measure? So do you take the a set of coordinates and then measure the entropy from some probability distribution, or you marginal? But then you also have this problem that if you take a probability distribution over, then you have this splitting problem, you know, that you have to, you split the system always in the same point, and that I think makes not really much sense. So then you have to take some kind of local version of entropy, pointwise maybe. So you take the, but that's just the log probability, the negative log probability. Yeah, I think like that, for example, I think it's not a bad idea to take the negative log probability of a spatial temporal pattern and say, okay, if this is very, right, if I take the negative, yeah, if it's very low, then maybe that's an agent, but yeah.
Where is the threshold?
Yeah, no, they should not be. I mean, like, there should not be. It should just be like levels of agency. But yeah, you would, yeah, then you would, so you could use this, for example, as an individuality criterion, and then you could still try to, you would still have to try to figure out if these things, which of these things have actions and perception, or and whether they're goal directed. But yeah, it's yeah. So, Fernando.
So could you do an imaginary exercise that you wake up one morning, you realize right definition? What would you do?
Ah, okay. So what would I do with it? So I would actually, okay, the truth, I can't think of some something very smart, so I just tell you the truth, which is that I would try to figure out whether it's possible that there are quantum agents and whether they would also think with the same logic as we do. And then if I would be done with that, I would stop being a scientist. No, I don't know. I mean, then actually I'm at the end. Yeah, I don't really know. Like, it's, for me, it's mostly because I want to understand what I am. Like, that's kind of my motivation to understand agents. It's like, why am I thinking like this? Am I thinking like this because of the laws of because the laws of physics are like this? Would I be thinking differently? Like, would my thought process have to change if the laws of physics were different? Or is this kind of mode of thinking, and for example, also mathematics, is it basically independent of the physical system that you exist in? And that's why I would want to look at quantum mechanics, because quantum mechanics is, of course, a bit different. And then you could check if you would be forced to think differently and get, I don't know, do something different, do different math. I don't really think, like, my intuition is no, the math would be the same. but I want to prove it. Maybe. Does Larissa want to add?
Well, I have two comments. So one is that, I mean, if you look at in the ancient times, people looked at the stars and then they saw them. I mean, how the constellations came about is a little bit like they saw this spatio-temporal pattern. They would slowly move, and they gave them agency, like Araya the hunter or whatever.
Mm-hmm.
So in that sense, you could say that maybe it's our human nature. That also it's very interesting that they imposed, I would call them kind of stars, like from their experience, like hunting or the animal thing they saw in their daily life, and they projected them onto those spatio-temporal patterns.
Mm-hmm.
So I think that's just a comment I want to make, that if you see some connection with that. And second is that, I'll say both things, then you can respond to them. The second comment is that, you know, on the other side, you can look at a holistic approach, that everything is connected, and there is a movement towards saying that when you cut something into agent and environment, then you lose some information actually. So if you, and the interesting thing is that if you take a holistic view, then you can see that there are different ways to cut off the whole, you know, like, so you can have this as agent and that as an agent.
Yeah.
And that gives you different perspective. Actually, this is the work that I had done before, because I study metaphors, and I think metaphors provide you a different way to cut off the agency. So if you cut it up in unconventional ways, then sometimes you get new information which can be very helpful for solving a particular kind of problem.
Yeah, so I think also that agency is a lot of projection. Like also he mentioned also the ancient times where people also projected all kinds of agency into thunder and lightning, for example. And yeah, so I think I accept also that it's a lot of projection, and maybe it's just and in some way it's maybe pure projection, because I also don't think, because if you take the physics point of view, then okay, so there's just the laws of physics and that's it, and then I don't need to care about any of these agents. But still somehow, yeah, on the one hand, if you take like some more subjective point of view, then it makes sense to describe the world in terms of agents. But then, and we don't describe everything, like somehow there are things that we don't describe as agents, at least nowadays. I mean, maybe in some kind of animistic religions, everything has a spirit, and then you go into like this kind of panpsychism also. But somehow I think there are some things that make certain spatio-temporal patterns in this universe special, and I think life is such a pattern, and I think I kind of, yeah, I still think it is there. I mean, like I might, yeah, but I'm basically hoping that it's, or I'm basically betting that it's there, and betting that I can find it, and probably with information theory. But yeah, it might not be there in the end. I don't know. And the second, what's the second question? Yeah. So that I'm yeah. I think, yeah, I agree that there's all these perspectives, and yeah, maybe you also lose something, but yeah, I think, yeah, those are things we have to figure out. I mean, we have to figure out what's the best way to look at a system, and also in the end, I also agree, for example, that I would hope that there's something special also that's kind of independent of the coordinate system you pick. But yeah, that's also just a hope more than knowledge. Yeah. Okay. Larissa, do you want to ask a question? She's
maybe.
Yeah, I can even see you.
Okay, perfect. So I just have a technical question, a little bit about your diagram of the environment and the action and the sensors and the memory.
Yeah.
There was no arrow directly from the sensors at time t to the action at time t+1. would that make a difference, like having something like a reflex that's directly an action caused directly by sensor input?
Yeah, it's a fair question. I think it actually doesn't make a difference because you can always route this through the memory. I mean, but it's so maybe you know that you know the difference between Moore and what are the other ones called? There are two kinds of automata architectures, and one are called Moore, and the other one are called. So one basically have this edge from the input directly to the output, and one or the inputs go first through the internal state. And you can prove that they are mathematically identical. So the set of things, the set of input-output behaviors that they can realize are actually identical. And I think this also carries over to the stochastic regime. You have to, so basically this memory state will probably have to have higher capacity than in the case where you have this edge directly. But it should be possible to get exactly the same behavior that you can get with the other setup. And there's one reason why I like this a little bit better, and that's that if you marginalize out, basically no, that's if you how do you say this? So if you know in this setup that I use, if you know the environment state and the memory state, then they together they form a Markov chain. So you don't need to know the action and the sensor state specifically to get the Markov chain. The action and sensor they're a bit like virtual in some way from this perspective. Yeah. That's the only reason why I like this a little bit better, because I get this global Markov chain then in the end, which I like because then I can say it's the universe. Yeah, that's basically it.
Thank you.